In 2021, a team at Los Alamos National Laboratory made the most precise measurement in the history of nuclear physics. They trapped ultra-cold neutrons, particles moving so slowly you could outrun them on a bicycle, inside a magnetic bathtub cooled to near absolute zero. They counted how many neutrons went in. They waited. They counted how many came out. And from this, they calculated exactly how long a free neutron lives before it decays. The answer was 877.75 seconds, give or take about a third of a second, roughly 14 minutes and 38 seconds. That number would be unremarkable, except for one thing: a completely different experiment at the National Institute of Standards and Technology, using a completely different method, has been measuring the neutron lifetime for decades. And they keep getting a different answer. Not wildly different, not off by minutes or even by a full percentage point. The NISBEAM experiment says the neutron lives 888 seconds, 14 minutes and 48 seconds, 9 seconds longer. That might not sound like much, but in precision physics, 9 seconds is enormous. The statistical significance of this disagreement is 4.4 sigma, which means there is roughly a 1 in 100,000 chance it is a fluke. The two methods have been refined, rebuilt, cross-checked, and scrutinized for 25 years. The gap will not go away. So where do the missing neutrons go? In the bottle experiment, you count survivors. In the beam experiment, you count the protons that neutrons produce when they decay. If the bottle sees fewer survivors, that means neutrons are decaying at a certain rate. If the beam sees fewer protons, that should mean neutrons are decaying at the same rate. But the beam consistently detects fewer protons than the bottle predicts. It is as though roughly 1% of the neutrons in the beam experiment are decaying into something that does not produce a proton at all, something invisible, something that no detector in the building can see. In 2019, a theoretical physicist named Zurab Berejiani proposed an explanation that sounds like it belongs in science fiction. He suggested that those missing neutrons are not decaying. They are vanishing, oscillating spontaneously and silently into an identical particle that exists in a completely separate sector of physics, a mirror neutron, a neutron made of mirror matter. And if Berejiani is right, those 9 missing seconds are not a measurement error. They are the first experimental hint that there is an entire invisible universe occupying the same space as ours, built from the same laws of physics, made of the same types of particles, running on its own complete set of forces, an entire cosmos that we cannot see, cannot touch, and can barely detect because its photons are not our photons, its atoms are not our atoms, and the only thing connecting the two worlds is gravity, and a coupling so faint it is 10 billion times weaker than ordinary electromagnetism. That is the idea at the center of this story. And the question we are going to spend the next hour trying to answer is deceptively simple. Is there a complete invisible universe sharing our space right now? And if so, why has every attempt to prove it exists come up empty? But to understand where this idea came from and why serious physicists still take it seriously, despite decades of null results, we need to go back to the moment when physics itself broke in half. We need to go back to 1956, to a laboratory at Columbia University, and to a woman who shattered one of the deepest assumptions in the history of science. In the early 1950s, physics had a problem it could not solve, and the problem had a deceptively simple name. It was called the Tau-Theta puzzle. Cosmic ray experiments and the new generation of particle accelerators had discovered two particles that appeared to be absolutely identical. Same mass, same spin, same lifetime, same electric charge. By every measure physicists could apply, tau and theta were the same particle. There was just one catch. Theta decayed into 2 pions, and tau decayed into 3 pions. 2 pions give you a positive parity. 3 pions give you a negative parity. And parity, in 1953, was sacred. For nearly 30 years, every physicist in the world had assumed that the laws of physics look the same in a mirror. If you run any experiment and then run it again, with everything reflected left to right, you should get exactly the same results. This principle, called parity conservation, had been proven rigorously for electromagnetism by Eugene Wagner back in 1927. The strong nuclear force also appeared to conserve parity. When the weak nuclear force entered the picture, everyone simply assumed it did too. Nobody tested it. Nobody even thought to test it, because the idea that the universe could tell left from right seemed absurd. So if parity was conserved, tau and theta could not be the same particle. They had to be two different particles that just happened to look identical in every other way. By 1956, this explanation was starting to feel absurd too. At the 6th Rochester Conference in April of that year, J. Robert Oppenheimer captured the mood perfectly. He said the Tau Meson would have either domestic or foreign complications, but it would not be simple on both fronts. During the same conference, Richard Feynman relayed a question from experimentalist Martin Bloch. Could it be, Bloch asked, that parity is simply not conserved? The room did not take the question seriously, but 2 young physicists did. Tsung-Dao Lee and Chen-Ning were both Chinese-born theorists at Columbia and Princeton. They had already published 32 papers together by that point, and they were about to write the most important one of their careers. After the conference, Lee had a key conversation with Jack Steinberger, and something clicked. He and Yang went back through every experiment ever performed on the weak nuclear force and made a stunning discovery. Not a single one of them had ever tested whether parity was conserved in weak interactions. The assumption was completely untested. 3 decades of confidence, resting on precisely 0 experimental evidence. Their paper landed like a grenade. Question of Parity Conservation in Weak Interactions, published in the Physical Review in October 1956. In it, Lee and Yang demonstrated the total absence of evidence and proposed specific experiments to settle the matter, including measuring beta decay from polarized cobalt-60 nuclei. If parity was violated, the electrons from the decay would come out preferentially in one direction rather than the other. If parity was conserved, they would come out symmetrically. The physics community was skeptical, to put it mildly. Freeman Dyson later admitted he read the paper twice, thought it was very interesting, and completely failed to grasp how important it was. Wolfgang Pauli was more direct. On January 17, 1957, he wrote a letter to Victor Weisskopf that included what might be the most spectacularly wrong prediction in the history of physics. I do not believe that the Lord is a weak left-hander, Pauli wrote. and I am ready to bet a very large sum that the experiments will give symmetric results. But here is the thing about Parity's letter. The date matters. January 17th, 1957. 2 days earlier, on January 15th, Columbia University had already held a press conference announcing that Parity was dead. The experiment had been done. The results were in. And Parity, sitting in Zurich, had not yet heard the news. He wrote his confident prediction into a void that had already been filled by reality. The woman who filled it was Chien-Shiung Wu. Wu was born in 1912 near Shanghai. Her father, an engineer and intellectual, had founded one of the first schools in China that admitted girls. She graduated top of her class from National Central University in Nanjing, came to the United States in 1936, earned her PhD at Berkeley under Ernest O. Lawrence, and joined Columbia University in 1944, where she worked on uranium enrichment for the Manhattan Project. By the mid-1950s, she was the world's foremost expert on beta decay, the very process Li and Yang's proposed test would measure. When Li visited Wu's office in the spring of 1956 and described the Parity test, she recognized what she later called a golden opportunity. She had been planning her first trip back to China in 20 years. She cancelled it. This was a golden opportunity for a beta decay physicist to perform a crucial test, she said, and how could I let it pass? The experiment required cooling cobalt-60 nuclei to 1/100th of a degree above absolute zero. That is a temperature so cold it makes outer space look warm. The cosmic microwave background sits at 2.7 Kelvin. Wu needed to reach 0.01 Kelvin, nearly 300 times colder than the vacuum between galaxies. At that temperature, and under a strong magnetic field, the cobalt nuclei would all align their spins in one direction. If parity was conserved, electrons from beta decay would fly out equally in both directions along the spin axis. Wu partnered with a cryogenics team at the National Bureau of Standards, Ernest Ambler, Raymond Hayward, Dale Hobbs, and Ralph Hudson. For months, they fought a maddening technical battle. Superfluid helium kept finding ways around the vacuum seals. Hobbs slept beside the apparatus, calling the others when temperatures were finally low enough to run. On December 27, 1956, they got their result. It was not subtle. It was not ambiguous. More electrons came out opposite to the nuclear spin than along it. The asymmetry was enormous and unmistakable. Parity was violated, spectacularly and beyond any reasonable doubt. On January 9th, at 2 a.m, Ralph Hudson produced a bottle of Chateau Lafite Rothschild, 1949 vintage, and they drank a toast. They had just proven that the universe is not symmetric. Nature knows the difference between left and right. The mirror, as a metaphor for fundamental physics, was broken. The confirmation came almost immediately. At Columbia, Leon Lederman and Richard Garwin heard about Wu's result at a Friday lunch on January 4th. That evening, Lederman called Garwin at home. They realized the muon beam at Columbia's Nevis cyclotron was already polarized. Using improvised equipment, including a coffee can, a wooden cutting board, and Scotch tape, they measured pion-muon electron decay asymmetry. By Tuesday morning, January 8th, they had a result at 50 standard deviations. Lederman called Lee and said 2 words: "Parity is dead." When Pauly finally heard the news, his reaction passed through several stages. First, "That's total nonsense. Then, when assured it was confirmed, then it must be repeated. And finally, in a follow-up letter to Weisskopf, now, after the initial shock, I'm starting to pull myself together. Richard Feynman, who had bet Norman Ramsey $50 to 1 that Parity would be conserved, quietly paid up. Li and Yang received the Nobel Prize in Physics that same year, 1957. One of the fastest Nobel recognitions in history, roughly 11 months after Wu's experimental confirmation. Wu was not included. Think about that for a second. Wu designed the experiment. Wu performed the experiment. Wu produced the result that confirmed the theory. She received at least 26 Nobel nominations between 1958 and 1973. Jack Steinberger, himself a Nobel laureate, frequently called it the biggest mistake of the Nobel Committee. Dale Hopps, Wu's collaborator, said she probably regretted her absence to the last day of her life. Wu went on to become the first woman president of the American Physical Society. She won the inaugural Wolf Prize in Physics. She was called the First Lady of Physics and the Chinese Madame Curie. She died in 1997 at age 84. In 2021, the United States Postal Service finally put her on a stamp. But the Nobel was never corrected. And there is a deeper irony here, one that matters for the rest of this story. In the same burst of work that led to the Parity paper, Li and Yang published a companion paper that almost nobody remembers. It was titled Possible Interference Phenomena Between Parity Doublets, and it explored a radical idea. What if parity is not really violated at all? What if every particle that appears left-handed has a hidden partner that is right-handed? What if, for every particle in our world, there exists a mirror twin, restoring the symmetry at a deeper level than anyone had imagined? That paper, published in 1956, is the intellectual seed of mirror matter theory. Li and Yang did not just break the mirror. They immediately proposed a way to fix it. And the fix would take 60 years to fully explore, leading physicists down a path toward an invisible universe that might be the answer to one of the biggest mysteries in all of science. But first, someone had to figure out what a mirror world would actually look like. A decade after Li and Yang's Parity doublets paper, 3 Soviet physicists in Moscow did something that would quietly reshape the boundaries of theoretical physics. They took the mirror idea seriously and followed it all the way to its logical conclusion. Igor Kobzarev, Lev Okun, and Isaac Pomeranchuk worked at the Institute of Theoretical and Experimental Physics in Moscow, one of the great powerhouses of Soviet theoretical physics. Okun was among the most influential particle physicists of his generation. He had coined the word hadron at a conference in 1962, a term that is now standard vocabulary for every physicist alive. Pomeranchuk was a legend, a student of Lev Landau. He had founded the theory division at ITEB, contributed fundamental results in quantum field theory, and had both a cooling technique and a reggae trajectory named after him. These were not fringe scientists chasing speculative ideas. These were giants of the field. Their 1966 paper, published in the Soviet journal Yadernaya Fizika, or Nuclear Physics, carried the dry title On the Possibility of Experimental Observation of Mirror Particles. But its content changed the field. They took Li and Yang's mirror partners and made a critical recognition that the original paper had missed. Mirror particles cannot share our forces. They cannot interact through our electromagnetism, our strong force, or our weak force. The mirror sector must have its own complete, independent set of all four fundamental interactions: mirror electromagnetism, mirror strong force, mirror weak force, mirror gravity. The only bridge between the two worlds is ordinary gravity, which curves space-time for both sectors equally. They called it the mirror world. The term itself was new. There is a poignant detail here that the history books usually skip. Pomeranchuk was dying. He had been diagnosed with esophageal cancer, and by late 1966, he was fading rapidly. He completed his last scientific paper 2 days before his death on December 14th. The mirror matter paper was published that same year. It was among the final works of his career. And here is where the irony gets almost unbearable. As Sergei Blinnikov later pointed out, Kobzarev, Okun, and Pomeranchuk had no idea about the work of Fritz Zwicky or Jan Oort, the astronomers who had been arguing since the 1930s that the universe contained far more mass than anyone could see. The Soviet physicists proposed a form of invisible, gravitationally interacting matter for purely theoretical reasons to restore a broken symmetry without knowing that observational astronomy was already screaming that such matter had to exist. They accidentally proposed a dark matter candidate before they knew dark matter was a problem. But the mirror world idea sat mostly dormant for 25 years. It circulated in Soviet physics circles. Blinnikov and Klopov made the explicit connection to dark matter in 1982. Bob Holdham at the University of Toronto proposed in 1986 that the ordinary photon and the mirror photon could undergo a subtle quantum mixing, creating an incredibly faint bridge between the two sectors beyond just gravity. But none of this attracted much attention in the West. Then, on a sunny afternoon in May of 1991, a young Australian physicist named Robert Foote had what he later described as a eureka moment. While playing with an unrelated idea, it suddenly struck him that there was a subtle yet simple way in which mirror reflection symmetry could still exist in nature, even though the weak force clearly violates parity. The key insight was that you do not need the mirror particles to live in our sector. You need an entirely separate copy of the standard model, connected to ours by a discrete symmetry that swaps left and right. Foote, along with Henry Liu and Raymond Volkas, published the modern formalization of mirror matter theory. That same year, their paper laid out the mathematics precisely. You take the entire standard model, every quark, every lepton, every gauge boson, the Higgs, all of it, and you duplicate it. The duplicate has opposite chirality. Left-handed particles in our world become right-handed particles in the mirror world. The two sectors are connected by a Z2 parity symmetry. If this symmetry is exact, every mirror particle has exactly the same mass as its ordinary counterpart. Mirror electrons weigh the same as electrons. Mirror protons weigh the same as protons. Mirror hydrogen behaves chemically just like hydrogen, except you will never see it because mirror photons are not our photons. The totality of what this implies is staggering. If mirror matter exists, it doubles the entire particle content of the universe. Not one new particle, not a handful, an entire parallel physics, mirror atoms, mirror molecules, mirror chemistry, mirror stars, mirror planets. As Lev Okun put it decades earlier, under favorable conditions, the mirror world could contain invisible mirror life. But here is the critical difference between mirror matter and every other dark matter candidate you have heard of. WIMPs, axions, sterile neutrinos. Those are all proposals for a single new particle, or at most, a small family of new particles, invented specifically to solve the dark matter problem. Mirror matter was not invented for dark matter. It was invented to fix a broken symmetry. The fact that it happens to produce an enormous amount of invisible, gravitationally interacting matter is either the most beautiful coincidence in physics or the deepest clue we have ever been handed about the nature of reality. Robert Foote spent the next 3 decades following that clue. He published roughly 100 papers on mirror matter. He wrote a popular book called Shadowlands. He proposed that mirror matter could explain the annual modulation signal in the Dharma dark matter detector. He suggested that the 1908 Tunguska explosion, the event that flattened 2,000 square kilometers of Siberian forest and 80 million trees with the force of 1,000 Hiroshima bombs while leaving no crater and no meteorite fragments, was caused by a mirror matter asteroid plowing through the atmosphere. Howard Georgi of Harvard captured the mainstream reaction when he said that Foote's ideas had not attracted a huge following, perhaps because the problems they solve, while interesting, are not the most critical puzzles the community is wrestling with. That assessment was about to change, because as Foote was building his case for the mirror world from the theory side, the observational case for dark matter was becoming so overwhelming that the physics community could no longer afford to ignore any viable candidate. And mirror matter, whatever else you might say about it, was undeniably viable. Let us talk about dark matter for a moment, because this is where the stakes get real. Dark matter is not a hypothesis. The hypothesis is what dark matter is made of. The existence of dark matter itself is one of the most thoroughly established facts in modern science, supported by at least 4 completely independent lines of evidence that all point to the same conclusion. Roughly 84% of all the matter in the universe is invisible. The first line of evidence goes back to 1933, when Swiss astronomer Fritz Zwicky was studying the Coma cluster, a swarm of over 1,000 galaxies about 320 million light-years away. Zwicky measured how fast the galaxies in the cluster were moving and used their speeds to calculate how much mass the cluster needed to hold itself together gravitationally. Then he compared that to the mass he could actually see: the stars, the gas, the dust. The numbers were off by a factor of roughly 400. The cluster needed 400 times more mass than was visible. Zwicky called the missing stuff dunkle Materie, dark matter, and for decades, almost nobody took him seriously. Then, in the 1970s, Vera Rubin and Ken Ford started measuring how fast stars orbit within individual galaxies. If most of a galaxy's mass is concentrated in the visible disk, stars at the outer edges should orbit slowly, the same way Pluto moves much more slowly than Mercury. But that is not what Rubin and Ford found. Star after star, galaxy after galaxy, the rotation curves came out flat. Stars at the edges of galaxies were orbiting just as fast as stars near the center. This is only possible if each galaxy is embedded in an enormous halo of invisible mass that extends far beyond the visible disk. Rubin measured 21 spiral galaxies. Every single one showed the same pattern. The third line of evidence is the bullet cluster, observed in 2006. Two galaxy clusters collided. When galaxy clusters collide, the hot gas in each cluster slams together and slows down, like two clouds of steam hitting each other. But the individual galaxies and any dark matter pass right through. By mapping the gravitational lensing of background galaxies, astronomers could see where the mass actually was. It was not where the hot gas was. It had passed right through, separated cleanly from the ordinary matter. The probability of this pattern occurring by chance, if dark matter does not exist, is roughly 1 in 10 to the 15th power, 1 in a quadrillion. And the fourth line is the cosmic microwave background, the afterglow of the Big Bang, measured with exquisite precision by the Planck satellite in 2018. The pattern of temperature fluctuations in this ancient light encodes the exact composition of the early universe. Planck's answer is unambiguous. The universe is roughly 26.4% dark matter, 4.9% ordinary matter, and 68.5% dark energy. Dark matter outweighs everything you can see, everything you have ever touched, every star, every planet, every atom in your body by a factor of more than 5 to 1. So that is the backdrop against which mirror matter enters the dark matter race. And it enters with some genuinely remarkable strengths. The most important one is self-interaction. The leading dark matter candidate for 40 years was the WIMP, the weakly interacting massive particle. WIMPs are essentially collisionless. They do not bounce off each other, do not form structures, do not do anything interesting. They just sit there and gravitate. And this creates problems. Computer simulations of collisionless cold dark matter predict that dark matter halos should have sharp, cuspy density peaks at their centers. Observations show flat cores instead. The simulations predict hundreds of satellite galaxies around something like the Milky Way. We observe roughly 50. The simulations predict that the biggest dark matter clumps should always contain visible galaxies. Some of them do not. These are called the core cusp problem, the missing satellites problem, and the too big to fail problem. And they have been thorns in the side of WIMP-based cosmology for years. Mirror matter solves all three naturally because mirror matter interacts with itself through mirror electromagnetism. Mirror atoms can collide, scatter, and redistribute energy, just like ordinary atoms do. This smooths out the cuspy centers into flat cores. It reduces the number of small satellite halos that survive, and it changes the density structure of the biggest halos in exactly the right way. The cross-section for these self-interactions is velocity-dependent, strong in small, slow-moving dwarf galaxies, and weak in large, fast-moving galaxy clusters, which is precisely the pattern observations require. No fine-tuning needed. It just falls out of the physics. But the self-interaction is not even the most striking part. The strangest thing about mirror matter as dark matter is what Big Bang nucleosynthesis does to it. If the mirror sector had the same temperature as the ordinary sector during the Big Bang, it would have contributed too many relativistic particles, screwing up the predicted abundances of helium and deuterium that we measure today. The mirror sector has to be colder. Specifically, the temperature of the mirror sector needs to be less than about 30 to 50% of the temperature of the ordinary sector. This is not ad hoc. It falls naturally out of many inflationary models, where the two sectors reheat to different temperatures after inflation ends. But the consequence of a colder mirror sector is profound. Lower temperature means mirror Big Bang nucleosynthesis proceeds differently. In our universe, roughly 75% of ordinary matter emerged from the Big Bang as hydrogen and about 25% as helium. In the cooler mirror sector, the balance flips. Mirror matter comes out roughly 75 to 80% mirror helium, with very little mirror hydrogen. The mirror universe is chemically inverted. It is a helium-dominated cosmos. Think about what that means. If mirror matter makes up the dark matter in our galaxy, then the invisible stuff flying through this room at 220 kilometers per second is not mirror hydrogen, not mirror water, not mirror anything familiar. It is mostly mirror helium, an entirely different chemical basis for an entirely different invisible world. And that difference is not a bug. It is a prediction that, in principle, changes how mirror dark matter interacts with detectors, how it forms structures, and how it behaves in collisions. It is, eventually, testable. So mirror matter explains dark matter's gravitational effects. It solves the small-scale structure problems. It makes specific, falsifiable predictions about the chemistry of the dark sector. And it was not even invented for dark matter. It was invented to fix a broken symmetry from 1956. Which brings us to the obvious question. If mirror matter is this good a candidate, why has nobody found it? Where is the evidence? Where is the smoking gun? This is where the story gets uncomfortable, because physicists have been looking, and they keep finding nothing. Let us come back to those 9 missing seconds. Zurab Bereziani was born in 1956 in Tbilisi, Georgia, then part of the Soviet Union. He studied physics at Tbilisi State University, earned his PhD in 1984, and eventually made his way to Italy, where he became a full professor at the University of L'Aquila, with an appointment at the Gran Sasso National Laboratory, one of the world's premier underground physics facilities. His publication record runs to over 10,000 citations and an H-index of 58. He is not a crank, and one of his first master's students back in Tbilisi in 1987 was Gia Dvali, who went on to become the director of the Max Planck Institute for Physics in Munich. Whatever you think of mirror matter, the people working on it are serious physicists. In 2005, Bereziani had an insight that changed the game. He realized that if mirror matter exists, there is one particle that might actually be able to cross the boundary between the two sectors: the neutron. It is electrically neutral, which is critical because a charged particle like the proton would have wildly different electromagnetic self-energies in the two sectors, making any transition between them effectively impossible. The neutron has a small magnetic moment, but that can be controlled with external fields, and quantum mechanics allows a process called oscillation, where a particle can spontaneously transform into a different particle if there exists a tiny coupling between the two states. Neutrinos do this all the time. They change flavor as they travel. Bereziani proposed that neutrons might do something similar, transforming into their mirror twins and vanishing from our world entirely. His paper with Luis Bento, published in Physical Review Letters, in 2006 showed that the oscillation time could be surprisingly short. Not billions of years, not millions of seconds, possibly as short as 1 second. Far shorter than the neutron's roughly 880-second decay lifetime. If this is correct, then any experiment that stores free neutrons for hundreds of seconds should see some of them simply disappear, converting into mirror neutrons that pass through the walls of the container and drift away invisibly. But there is a catch, and it is a crucial one. The oscillation is exquisitely sensitive to magnetic fields. Even the Earth's modest magnetic field, roughly half a Gauss, creates a tiny energy difference between the neutron and the mirror neutron, because the neutron has a magnetic moment that couples to ordinary magnetic fields, while the mirror neutron does not. This energy splitting suppresses the oscillation dramatically. In a zero-field environment, the transition can proceed freely, but turn on even a small magnetic field, and it effectively freezes. This is where Bereziani's explanation of the neutron lifetime puzzle gets clever. Remember, the bottle experiments that give the shorter lifetime operate at very small magnetic fields, close to zero. Under those conditions, if any neutrons convert to mirror neutrons, they simply escape the trap and are counted as having decayed. But the fractional loss is tiny, less than 1 in a million, over a few hundred seconds, so the measured lifetime is essentially correct. It matches the standard model prediction. The beam experiment is different. The beam passes through a proton-counting trap, surrounded by a solenoid producing 4 to 5 Tesla. That is roughly 10,000 times the strength of Earth's magnetic field. Normally, this strong field would suppress oscillations completely, but Bereziani realized there is an exception. If the neutron and mirror neutron have a very small mass difference, roughly 100 to 300 nanoelectron volts, then at certain magnetic field strengths, the energy splitting from the magnetic field exactly matches the mass splitting. At that resonance point, the oscillation probability spikes. The neutron and mirror neutron energy levels cross, and a quantum mechanical process called the Landau-Zener transition kicks in. As neutrons travel through the varying magnetic field profile in the beam apparatus, roughly 1% of them convert to mirror neutrons. Those mirror neutrons decay invisibly. Mirror proton, mirror electron, mirror antineutrino, none of which register in any detector. The result is 1% fewer protons than expected, which makes the apparent lifetime about 1% longer. 1% of 878 seconds is almost exactly 9 seconds. That is elegant, almost suspiciously elegant. But is it true? This is where we have to be honest about what experiments have actually found. And what they have found so far is nothing. The first direct search for neutron to mirror neutron oscillations was conducted at the Institut Loewe-Langevin in Grenoble, France, in 2007. They trapped ultra-cold neutrons in a storage chamber, varied the magnetic field, and looked for anomalous losses that would indicate neutrons converting to mirror neutrons. The result was a lower limit on the oscillation time of 103 seconds, meaning if the oscillation happens at all, it takes at least that long. Subsequent experiments pushed the limit higher. The strongest constraint from ultra-cold neutron storage, assuming no mirror magnetic field is present, now stands at 448 seconds. That means If you put a neutron in a box with zero magnetic field, it will sit there for at least 7.5 minutes before it has any significant probability of converting to a mirror neutron. But Beregiani pointed out a loophole that keeps the idea alive. If a mirror magnetic field exists in the laboratory, and there is no reason in principle why there could not be one if mirror matter pervades the galaxy, then the constraints change dramatically. With a mirror magnetic field present, the limits drop to as low as 17 seconds. And for specific combinations of mirror field strength and orientation, oscillation times as short as roughly 1 second remain completely consistent with all existing data. The phenomenon could be happening vigorously and still escape detection in experiments not designed to probe the right field configurations. The most important recent experiments were conducted at the spallation neutron source at Oak Ridge National Laboratory in Tennessee. In 2022, Leah Broussard and her team used a cold neutron beam and a 6.6 Tesla magnet to look for neutron regeneration, a process where neutrons convert to mirror neutrons, pass through a wall, and then convert back. If mirror neutrons exist, you should see a faint signal of neutrons appearing on the far side of an impenetrable barrier. They found nothing. No regenerated neutrons above background. An improved version of the experiment, published in 2024 by Gonzalez, Rock, Broussard, and collaborators, reduced the background by a factor of 10 through better shielding. Again, nothing. The result specifically excluded the mirror neutron oscillation as an explanation for the neutron lifetime anomaly across a wide range of mass splittings in the models they tested. And then, in December 2024, the J-Park experiment in Japan threw another wrench into the story. Their beam experiment measured the neutron lifetime using electron detection instead of proton detection and got 877.2 seconds. That is consistent with the bottle experiments. It is in 2.3 sigma tension with the NIST proton counting beam result. This raises an uncomfortable possibility. Maybe the neutron lifetime puzzle is not new physics at all. Maybe it is a systematic error in one specific experiment's proton counting technique. If the J-Park result holds up, one of mirror matter's most compelling anomalies could simply evaporate. But here is why the story is not over. Even if the neutron lifetime puzzle turns out to be a measurement artifact, it does not kill mirror matter. The lifetime anomaly was never the primary argument for the mirror world. It was always just one data point, one possible hint in a much larger theoretical framework. Mirror matter was proposed in 1956 to fix a broken symmetry. It was formalized in 1966 as a complete hidden sector. It was connected to dark matter in 1982. It was given a modern mathematical foundation in 1991. The neutron lifetime puzzle did not appear until the late 1990s. If it goes away, the theory loses a potential piece of evidence, but the theory itself remains exactly as motivated as it was before the puzzle existed. And the search continues, because there is one experiment on the horizon that could change everything. In the south of Sweden, near the city of Lund, sits the European spallation source, the most powerful pulsed neutron facility ever built, and attached to it is an experiment called HIBEAM for high-intensity baryon extraction and measurement. Stage 1, running from roughly 2024 through 2028, will search for both neutron to anti-neutron oscillations and neutron to mirror neutron oscillations using the brightest neutron beam in the world. Stage 2, called NNBAR, planned for approximately 2030 through 2034, will improve sensitivity by more than 3 orders of magnitude over the best previous limits. That is a factor of 1,000. The collaboration involves more than 60 authors, and the detailed design papers were published in 2025. If mirror neutrons exist with oscillation times anywhere in the range that current data still allows, IBM should see them. If it does not, the remaining parameter space shrinks dramatically. This is not a vague promise of future sensitivity. The experiment is under construction right now, but mirror matter's story with experiment is not limited to neutron oscillations. There is another thread, one that involves the most controversial result in the history of dark matter detection. And it is worth pulling on because it tells you something important about how hard it is to find an invisible universe even when you are specifically looking for it. Deep underground, beneath 1,400 meters of rock in the Gran Sasso mountain in central Italy, sits a laboratory built inside a highway tunnel. The Laboratori Nazionali del Gran Sasso is one of the largest underground physics facilities in the world, and for more than 2 decades, it has been home to the most maddening experiment in all of dark matter science, the Dharma experiment, later upgraded and renamed Dharma/Libra. The idea behind Dharma is simple and beautiful. The Earth orbits the Sun. The Sun orbits the center of the Milky Way at about 220 kilometers per second, plowing through the galactic dark matter halo. In June, the Earth's orbital velocity adds to the Sun's galactic velocity, so we are moving through the dark matter slightly faster. In December, the Earth's orbital velocity subtracts from it, so we are moving slightly slower. If dark matter particles occasionally scatter off atomic nuclei in a detector, the detection rate should oscillate annually, peaking around June 2nd and reaching a minimum around December. Dharma/Libra uses 250 kilograms of sodium iodide crystals to look for exactly this signal, and they found it. They have been finding it for over 20 years. The annual modulation is observed at a statistical significance of 13.7 sigma over 22 annual cycles and nearly 3 ton-years of exposure. The amplitude, phase, and period all match the dark matter prediction. By normal standards of particle physics, where 5 sigma is considered a discovery, 13.7 sigma should be case closed, but it is not case closed because no other experiment has been able to reproduce the signal. COSINE 100, a sodium iodide experiment in South Korea designed specifically to test Dharma's result, found no signal in 2018. ANACE 112, another sodium iodide experiment in Spain, also found no signal in 2021. And then, in 2022, COSINE 100 did something devastating. They reanalyzed their data using Dharma's own analysis technique and found a modulation signal. But it had the opposite phase. It peaked in winter instead of summer. That is the signature of a systematic effect in the analysis, not of dark matter. Robert Foote had proposed that Dharma was detecting mirror dark matter. His argument was clever. Mirror atoms in the galactic halo, mostly mirror helium, mirror oxygen, and mirror iron, would scatter off sodium and iodine nuclei in the detector through photon-mirror-photon kinetic mixing. The required coupling was epsilon of roughly 4 × 10⁻⁹, tantalizingly close to the existing limits from Big Bang nucleosynthesis. Foot's model could explain why Dharma saw a signal, while other experiments using different target materials like xenon or germanium did not, because the Rutherford-like scattering from mirror atoms produces different energy spectra in different targets than the simple contact interaction expected from WIMPs. It was an elegant idea, but the cosine 100 opposite phase result largely demolished it. If the modulation is an artifact of the analysis method rather than a real physical signal, then there is nothing for mirror matter to explain. So that is another potential piece of evidence gone. The neutron lifetime puzzle may be a systematic. The Dharma signal appears to be an artifact. Two of the most talked about anomalies that mirror matter could have explained seem to be dissolving, and the broader experimental picture is similarly bleak. The search for dark photons, the mediator particle that would bridge the ordinary and mirror sectors, has produced nothing. FACER, the newest forward search experiment at the Large Hadron Collider, published its first results in 2023. 0 events observed in the signal region for dark photons with mixing parameters between about 2 × 10⁻⁵ and 1 × 10⁻⁴ for masses of 17 to 70 mega-electron-volts. NA62, the Kahn experiment at CERN running in beam dump mode, published exclusion results in 2024. Nothing. CMS, ATLAS, LHCb, all searching, all finding null results. The CDEX10 experiment in China has pushed limits on mirror matter specifically, excluding kinetic mixing above 2 × 10⁻⁻10 for mirror nuclear dark matter. But, and this is a critical but, significant parameter space remains open. The dark photon searches have mostly probed mixing parameters above 10⁻⁵, while mirror matter models typically predict values around 10⁻⁹ to 10⁻10. That is a gap of 4 to 5 orders of magnitude. The experiments have not yet reached the regime where mirror matter actually lives. It is like searching for a shipwreck in a harbor when the ship sank in the open ocean. Finding nothing in the harbor does not tell you the ship did not sink. Meanwhile, the 40-year search for WIMPs, the particle that was supposed to be dark matter, is approaching its endgame. The Large Underground Xenon-Zirconium Experiment, or LZ, located nearly a mile underground at the Sanford Underground Research Facility in South Dakota, is currently the most sensitive dark matter detector ever built. In 2025, it achieved world-leading sensitivity, pushing limits on WIMP nucleon cross-sections down to roughly 10⁻⁴ square centimeters at a mass of 36 GeV. To put that in perspective, the experiment can detect interactions so rare that they would happen less than once per year in 10 tons of liquid xenon. And despite this extraordinary sensitivity, LZ has not found a single WIMP. LZ did accomplish something remarkable though. It made the first statistically significant detection of solar neutrinos through coherent elastic neutrino nucleus scattering at 4.5 sigma. This matters because it means LZ is now entering what physicists call the neutrino fog, the regime where the background from solar neutrinos becomes indistinguishable from a potential WIMP signal. Every future WIMP search will have to contend with this irreducible background. The classical WIMP parameter space is being rapidly closed, and the era of simply building a bigger xenon tank and waiting is coming to an end. The same story is playing out for axions, another leading dark matter candidate motivated by an entirely different problem in physics called the strong CP problem. The ADMX experiment achieved DFSZ level sensitivity in 2025, meaning it can now detect the more weakly coupled of the two main axion models in a narrow frequency range around 3.3 microelectron volts. No axion was found. New approaches like MADMAX, a dielectric haloscope, published first results in 2025, but are still years from full sensitivity. The axion search is entering its most theoretically interesting parameter space, but so far, the cupboard is bare. Sterile neutrinos, once promising after a controversial 3.5 kilo-electron-volt X-ray line, was reported in galaxy cluster observations in 2014, have been largely disfavored. The line was not confirmed by XMM Newton blank sky surveys, and the astrophysical interpretations have multiplied without resolution. Primordial black holes remain viable in certain mass windows, but are constrained by microlensing surveys, gravitational wave observations, and cosmic microwave background limits to the point where they almost certainly cannot account for all of dark matter. The situation, as of 2025, is that no dark matter candidate has been confirmed by any experiment. Not WIMPs, not axions, not sterile neutrinos, not mirror matter, not anything. 84% of the matter in the universe remains completely unidentified. We know it is there. We can see its gravitational effects on every scale from dwarf galaxies to the cosmic microwave background, but we do not know what it is. And in this landscape of universal failure, mirror matter has one advantage that no other candidate can claim. It was not invented for dark matter. It was not designed to fit the observations. It was proposed in 1956 to fix a broken symmetry, formalized in 1966 as a hidden sector, and only later recognized as a dark matter candidate. Every other leading candidate, WIMPs, axions, sterile neutrinos, was specifically constructed to solve the dark matter problem. Mirror matter solves it as a side effect of solving something else. Whether that makes it more likely to be right or merely more aesthetically pleasing is a question that only experiment can answer, and the experiments that could answer it are running right now or will be within this decade. There is one more wrinkle worth pulling on before we get to the question of what the mirror universe would actually look like if it exists, and it involves a collision between the most precise measurements in cosmology and a version of mirror matter that has nothing to do with dark matter at all. In 2022, a team led by Zachariah Chacko published a paper examining the mirror twin Higgs model, a version of the mirror sector that was originally proposed to solve the hierarchy problem. The question of why the Higgs boson is so much lighter than the energy scale where gravity becomes important. The mirror twin Higgs posits a twin sector with its own complete copy of the standard model, linked to ours by a discrete symmetry, exactly like mirror matter. But it was proposed for a completely different reason. What Chacko and collaborators showed is that if roughly 20% of the dark matter in the universe consists of twin baryons, matter from this mirror-like sector, it can simultaneously relax two of the most stubborn tensions in modern cosmology. The first is the Hubble tension, the persistent disagreement between local and cosmic microwave background measurements of how fast the universe is expanding. The second is the S8 tension, a discrepancy in how clumpy the matter distribution in the universe is. The mirror twin Higgs model with twin dark matter was preferred over the standard cosmological model by roughly 4 sigma in certain datasets. This result did not prove mirror matter exists, but it got the attention of the mainstream physics community in a way that neutron oscillations and Dharma signals never quite did. The hierarchy problem is one of the central puzzles of particle physics. If the solution to that puzzle naturally produces a mirror sector that also happens to fix cosmological tensions, the idea starts to look less like a curiosity and more like something the universe might actually be telling us. The SNOMAS 2021 process, the decadal survey that sets priorities for American particle physics, explicitly called for a delve-deep, search-wide approach to dark matter that includes hidden sectors. The Particle Data Group's 2024 review of dark matter mentions mirror dark matter by name. Active research groups at L'Aquila, Oak Ridge, the University of Maryland, the Paul Scherrer Institute, and the ESS collaboration continue to publish. The field is small, maybe 3 to 5 groups worldwide. But it is not dead, and it is not fringe, and the null results have not killed it, because the experiments have not yet reached the parameter space where mirror matter actually predicts signals. And there is one more piece of data that refuses to go away quietly. In late 2025, an independent analysis combined data from both Xenon NT and LZ, the 2 most sensitive dark matter detectors on Earth, and found something unexpected. In the high-energy nuclear recoil region, where neither experiment expected to see dark matter signals based on standard WIMP models, there was an excess. The local statistical significance reached up to roughly 4 sigma. 4 sigma is not a discovery. 5 sigma is the standard threshold, and local significances routinely evaporate when you account for the many places you could have found a fluctuation. But the nature of the excess was intriguing. It was consistent with velocity-dependent or inelastic dark matter scattering, exactly the kind of scattering that self-interacting dark matter, like mirror matter, could produce. The interpretation depends heavily on the background from xenon 124, a naturally occurring isotope whose contribution at high energies is poorly understood. If the xenon 124 background is larger than assumed, the excess disappears. If it is not, then 2 independent detectors on 2 different continents may be seeing the same anomalous signal. Neither the Xenon on N or the LZ collaborations have claimed this as evidence of dark matter. They are cautious, as they should be. But the result warrants monitoring, and it is precisely the kind of signal that mirror matter models, with their velocity-dependent Rutherford-like scattering, could produce. So that is where the experimental story stands. As of early 2026, a list of null results, a couple of dissolved anomalies, one suggestive but ambiguous hint from direct detection, and a next-generation experiment under construction in Sweden that could settle the question of neutron oscillations within the decade. Not exactly a smoking gun, but not a closed case either. Which brings us to a question that is just as interesting as whether mirror matter exists. If it does exist, what does the mirror universe actually look like? This is where the physics goes from abstract to astonishing, because the mirror world, if it is real, is not just a vague fog of invisible particles drifting through space. It is a structured, complex, chemically distinct cosmos, and it is nothing like our own. Start with the temperature. We established earlier that the mirror sector has to be colder than our sector to be consistent with Big Bang nucleosynthesis. The temperature ratio has to be less than about 0.3 to 0.5, meaning the mirror photon background temperature is at most half the temperature of the ordinary cosmic microwave background. Ours is 2.7 Kelvin. The mirror one would be roughly 1 Kelvin or less, colder than liquid helium. This temperature difference cascades through everything. Mirror Big Bang nucleosynthesis, running at a lower temperature, produces a radically different chemical mix. In our universe, the primordial gas was about 75% hydrogen and 25% helium by mass. In the mirror sector, the ratio is essentially inverted, 75 to 80% mirror helium, very little mirror hydrogen. This is not a minor difference. It changes the entire character of the mirror cosmos. In our universe, hydrogen is the raw material for stars, for water, for organic chemistry, for life. Stars burn hydrogen into helium and then build heavier elements through fusion. In the mirror universe, the starting material is helium. Mirror stars would ignite differently, burn differently, evolve differently, and die differently. The mirror periodic table would still exist. Mirror nuclear physics would produce mirror carbon, mirror oxygen, mirror iron, all the same elements, but the pathways and timescales would change. The mirror universe might have stars. It might even have planets, but they would not be arranged like anything we recognize. And here is something that has genuinely bizarre implications. Mirror matter interacts with itself through mirror electromagnetism. That means mirror matter can radiate, not ordinary photons, mirror photons. It can cool, clump, and collapse into structures through dissipative processes, just like ordinary matter does. In the standard picture of collisionless dark matter, the dark stuff just sits in big puffy halos around galaxies. But if dark matter is mirror matter, it can form a disk, a dark disk, coplanar with or slightly tilted relative to the ordinary galactic disk. Some groups have calculated that up to 10 to 20% of mirror matter in a galaxy could settle into a thin, dense disk structure. If a dark disk exists in the Milky Way, the density of dark matter near the galactic plane, where the Earth orbits, could be significantly higher than the standard assumption of 0.3 giga-electronvolts per cubic centimeter. That would change the expected signal rates in every dark matter detector on Earth. It would also mean that twice per galactic orbit, as the Sun bobs above and below the midplane of the disk, the dark matter density the Earth passes through would vary. This is a prediction that is, in principle, testable with sufficiently sensitive direct detection experiments running over many years. Robert Foote took the mirror world idea further than anyone. His 2001 paper on the Tunguska event proposed that a body made of mirror matter, perhaps a mirror asteroid or a fragment of a mirror comet, entered the atmosphere on June 30th, 1908, over the Podkamennaya Tunguska River in Siberia. an ordinary asteroid of comparable size would have left a crater. No crater was ever found, despite multiple expeditions. An ordinary asteroid would have left meteorite fragments. None were found. An ordinary asteroid would have been visible on approach. No one reported seeing anything before the explosion. An airburst of ordinary material has been the default explanation since the 1961 Tunguska Conference, but it requires a stony or icy body to completely disintegrate at altitude, which is physically possible but debated. Foot's mirror matter hypothesis offers a different explanation. A mirror asteroid would be invisible to the eye and to radar. It would pass through the atmosphere with minimal friction because mirror atoms do not collide with ordinary air molecules. But through the tiny kinetic mixing interaction, it would deposit energy into ordinary air as it flew, heating the atmosphere along its path. The energy deposition would be proportional to the square of the mixing parameter and the cross-sectional area of the body. For a mirror asteroid with mass around 1 million tons and the right mixing parameter, the energy release would match the observed 3 to 15 megatons. The most exotic prediction is that the mirror asteroid would not have vaporized on impact. It would have plowed into the ground, invisible and intact, burying itself beneath the Siberian permafrost. Foot suggested that tons of mirror matter might still lie underground at the Tunguska site, detectable in principle by precision gravimetry, measuring the gravitational pull of an invisible mass beneath the surface. No such search has been conducted. The idea remains speculation, but it illustrates something important about mirror matter as a scientific hypothesis. It makes specific, testable predictions. The predictions are wild, yes. An invisible asteroid buried in Siberia, a dark disk in the Milky Way, a chemically inverted shadow universe dominated by helium, neutrons vanishing into a parallel sector. But they are predictions. They are not vague gestures at the unknown. They are concrete claims that future experiments and observations can confirm or reject. And this is what separates mirror matter from mere philosophy. It is falsifiable, barely, painfully, at the ragged edge of our experimental capabilities, but falsifiable. Let us now talk about what it would actually take to find it, because the experiments that could discover mirror matter are not hypothetical. They are either running right now, under construction, or in the planning stages. And the next decade is going to be decisive. The highest priority target is neutron to mirror neutron oscillation. High beam at the European spallation source is designed to be the definitive experiment. The ESS produces the world's most intense pulsed neutron beam, and high beam will use it to search for both neutron-antineutron and neutron-mirror-neutron transitions, with signal efficiency projected at 70 to 80% and background rejection exceeding 10 to the 9th power, which is 1 billion to 1. If mirror neutrons exist with oscillation times anywhere in the currently allowed range of roughly 1 to 500 seconds, high beam should find them within its first few years of operation. If it finds nothing, the allowed oscillation time gets pushed into the thousands of seconds, where the phenomenon becomes so slow it is essentially unobservable in laboratory settings. The second target is the neutron lifetime puzzle itself. The JPARC result from December 2024, which agrees with bottle experiments, needs to be confirmed with higher precision. The UCN Tau plus upgrade at Los Alamos aims for total uncertainty below 0.1 seconds. If the beam discrepancy truly collapses, it closes one of mirror matter's most suggestive anomalies. If it persists, Bereziani's magnetic resonance explanation becomes the leading candidate, and a dedicated test at the high-flux isotope reactor Oak Ridge, varying the magnetic field profile and looking for the predicted dramatic changes in conversion probability, could be the clincher. The third target is direct detection through kinetic mixing. This is the hardest because the mixing parameter is so tiny. At epsilon of 10 to the minus 10, the interaction between ordinary and mirror matter is 10 billion times weaker than electromagnetism. Detecting this requires detectors with extraordinary sensitivity at low energies and the ability to distinguish the Rutherford-like recoil spectrum of mirror atoms from the flat spectrum expected from WIMPs, or the known backgrounds from neutrinos. The current generation of xenon detectors is approaching this regime, but has not reached it. Next-generation experiments like Darwin, a proposed 50-ton xenon detector, could push into the parameter space where mirror matter signals are predicted. But Darwin is still in the planning phase and unlikely to take data before the early 2030s. The fourth target is cosmological. Mirror matter with dissipative interactions make specific predictions about galaxy formation, cluster dynamics, and the cosmic microwave background that differ from collisionless, cold dark matter. The Hubble tension and S8 tension, if they persist, provide indirect evidence for a self-interacting dark sector. The mirror twin Higgs model's 4 sigma preference over standard cosmology, while not definitive, is the kind of result that keeps entire research programs alive. Future cosmic surveys, including the Vera C. Rubin Observatory and the European Space Agency's Euclid mission, will map dark matter distributions with unprecedented precision and could distinguish between collisionless and self-interacting dark matter models. So the picture is this: mirror matter has not been found. Every direct search has returned a null result. 2 of its most promising anomalies, the neutron lifetime discrepancy and the Dharma signal, may be on their way to being explained by mundane causes, but the theoretical motivation is as strong as ever. The experimental parameter space is far from closed. The next generation of experiments can reach the regime where signals are predicted, and the universe's most stubborn cosmological tensions happen to align with what mirror matter models predict. The invisible universe has not been ruled out. It just has not been caught yet. Now, before we go any further, we need to clear up something that has probably been nagging at you if you know any physics at all. Because the word mirror is doing a lot of heavy lifting in this story, and it is almost certainly evoking the wrong picture in your head. Mirror matter is not antimatter. This is the single most common confusion, and it is not your fault. Pop science has spent decades describing antimatter as matter's mirror image, because a positron is an electron with its charge flipped, and an antiproton is a proton with its charge flipped, and it feels natural to call that a reflection. But the mirror in antimatter refers to charge conjugation, flipping the sign of electric charge. The mirror in mirror matter refers to parity, flipping left and right. These are completely different symmetry operations, and they produce completely different physics. When antimatter meets matter, it annihilates. A positron and an electron collide and convert their entire combined mass into gamma rays. This is real. We produce antimatter at CERN every day. We have trapped individual anti-hydrogen atoms and measured their properties. Antimatter is energetically violent and experimentally confirmed. Mirror matter does none of this. A mirror proton and an ordinary proton would pass through each other like ghosts. No annihilation, no gamma rays, no interaction at all beyond gravity and that absurdly faint kinetic mixing. Mirror matter is not the opposite of matter. It is the twin of matter, built from the same blueprint, but using a different set of force carriers. Antimatter has been observed since 1932. Mirror matter has never been observed at all. The second misconception is subtler, but just as important. Mirror matter is not in a parallel dimension. When the Oak Ridge neutron oscillation experiments made the news in 2022, multiple outlets described them as a search for a portal to a parallel universe. The researchers themselves had to publicly correct this. Leah Broussard and her collaborators were not looking for doorways to the upside down from Stranger Things. They were looking for neutrons converting into mirror neutrons right here, in our universe, in our space, in their laboratory. If mirror matter exists, it occupies the same 3 dimensions of space and 1 dimension of time that you do. It is not somewhere else. It is here, right here, in this room, in your body, passing through you at 220 kilometers per second as you read this. You cannot see it because its photons are not your photons. You cannot touch it because its atoms do not interact with your atoms electromagnetically. But it is not in another dimension any more than radio waves are in another dimension, just because you cannot see them with your eyes. Mirror matter is invisible, not absent. And the third misconception, the one that trips up even physics students, is about what the word mirror actually means in this context. It does not mean that mirror matter can be seen in a mirror. A mirror, the physical object in your bathroom, works by reflecting ordinary photons. Mirror matter emits and absorbs mirror photons, which do not interact with ordinary mirrors, ordinary eyes, ordinary cameras, or ordinary anything. You could fill a room floor to ceiling with mirror matter, and a mirror in that room would show you nothing. The word mirror refers exclusively to the parity transformation in particle physics, the mathematical operation that swaps left-handed and right-handed chirality. It is a metaphor from group theory, not from interior decorating. There is one more point worth correcting, and it is about parity violation itself. The discovery that the weak force violates parity does not mean that all of physics is asymmetric. Electromagnetism conserves parity perfectly. The strong nuclear force conserves parity. Gravity conserves parity. Out of the 4 fundamental interactions, only one, the weak force, distinguishes left from right. That is what made the discovery so shocking in 1957. It was not that physics was generally asymmetric. It was that one specific force, and only one, broke the rule that everyone assumed was universal. And it is worth noting that parity violation and CP violation are different things. CP violation, the discovery that the combined symmetry of charge conjugation and parity is also broken, came later, in 1964, when James Cronin and Val Fitch observed it in neutral Kahn decays. CP violation is related to parity violation, but is a distinct phenomenon with different implications. You can have parity violation without CP violation and vice versa. The mirror matter hypothesis addresses P violation specifically. CP violation is a separate headache with its own theoretical implications. The reason these corrections matter is not pedantic. They matter because the precise nature of the symmetry being discussed is the entire foundation of the theory. Mirror matter is not motivated by vague notions of duality or parallel worlds. It is motivated by a specific, mathematically precise symmetry operation, the parity transformation, and the specific, experimentally confirmed fact that one of the four fundamental forces violates it. The proposal is that this violation is not fundamental. It is an artifact of looking at only half the picture. The full picture, ordinary sector plus mirror sector, restores the symmetry at a deeper level. And to appreciate why physicists care so deeply about this particular symmetry, you need to understand something about how symmetry works in physics generally. Symmetries are not decorative. They are the load-bearing walls of the entire theoretical structure. Emmy Noether proved in 1918 that every continuous symmetry of physics corresponds to a conservation law. Time translation symmetry gives you conservation of energy. Spatial translation symmetry gives you conservation of momentum. Rotational symmetry gives you conservation of angular momentum. These are not observations. They are mathematical necessities. If the symmetry exists, the conservation law follows automatically. Parity is a discrete symmetry rather than a continuous one, so it does not produce a conservation law in the same way, but it produces something equally important. It constrains which processes are allowed and which are forbidden. If parity is conserved, certain decay modes simply cannot happen. Certain correlations between spin and momentum are impossible. The moment you discover that parity is violated, those constraints evaporate, and you have to reconsider everything you thought you knew about the processes governed by the weak force. Now, most physicists responded to parity violation by simply accepting it. The weak force is left-handed. Fine, that is just how it is. But there is a deeper question, and it is the question that has driven mirror matter theorists for 7 decades. Why is it just how it is? Why should one of the 4 fundamental forces break a symmetry that the other 3 respect? Is there a reason, or is it just an accident? If you believe that fundamental physics should be symmetric, if you believe that the laws of nature should not have arbitrary, built-in preferences for left over right, then mirror matter is not an exotic hypothesis. It is the conservative one. It is the proposal that says the asymmetry is apparent, not real. The universe is symmetric. We are just looking at half of it. The alternative is that the universe simply has a preferred handedness baked into its fundamental laws for no reason at all. That parity violation is just a brute fact, like the value of the electron mass or the strength of the gravitational constant, something we measure but cannot explain. Most working physicists lean toward this view, at least implicitly. They accept parity violation as given and move on. But the mirror matter community insists there might be a deeper answer, and they have been searching for evidence for longer than most of their colleagues have been alive. Now, let us return to the people. We left Li and Yang at the peak of their triumph. Nobel Prize at ages 30 and 35, one of the fastest recognitions in the history of the award. two young Chinese-born physicists who had cracked open one of the deepest assumptions in science. You would think this would be the beginning of a legendary partnership. Instead, it was the end. Li and Yang had published 32 papers together. They had complementary strengths. Li was the more intuitive physicist, the one who often had the initial insight. Yang was the more mathematical, the one who could formalize and generalize. Together, they were formidable. But the question of who contributed what, and who deserved more credit for the Parity work specifically, became a wound that never healed. The trigger was a New Yorker article. On May 12, 1962, Jeremy Bernstein published A Question of Parity, a profile that, in Yang's view, misrepresented their respective contributions. On April 18th of that year, Li and Yang had an intensely emotional meeting. The details of what was said have never been made fully public. What is public is the outcome. They never collaborated again. Not one paper in the remaining 62 years of Li's life and 63 years of Yang's. In 2002, Yang was asked about the possibility of reconciliation. His answer was blunt. It is not necessary for me to reconcile with Li. And so, two men who together made one of the most important discoveries in 20th century physics spent the rest of their lives, decades upon decades, not speaking to each other. Li died in August 2024 in San Francisco at age 97. Yang died in October 2025 in Beijing at age 103. They were estranged to the end. Yang's life after the split was extraordinary in its own right. Beyond parity violation, his most profound contribution to physics was Yang-Mills theory, published in 1954 with Robert Mills. At the time, almost nobody paid attention. It seemed like a mathematical exercise without physical application. But Yang-Mills theory turned out to be the mathematical foundation of the entire standard model of particle physics. The strong force, the weak force, the electroweak unification, all of them are Yang-Mills gauge theories. It is arguably the most important single contribution to theoretical physics in the second half of the 20th century. And it came from the same mind that helped break parity and propose its restoration through mirror matter. Yang returned permanently to China after his retirement from Stony Brook in 1999. In 2004, at age 82, he married Weng Fan, a 28-year-old graduate student. The 54-year age gap caused a sensation in Chinese media. In 2015, he renounced his American citizenship to become a Chinese citizen, explaining that his father had never forgiven him for taking American citizenship in the first place. He turned 100 on October 1st, 2022, and died 3 years later, still celebrated in China as one of the greatest scientists in the nation's history. Li, for his part, devoted much of his later career to fostering physics in China. He helped establish the Beijing Electron-Positron Collider and created the Q-SPARE program, which brought hundreds of Chinese physics students to American graduate schools in the 1980s and 90s. Many of those students went on to lead major research programs on both sides of the Pacific. His legacy in Chinese science may ultimately be as significant as his contributions to particle physics. But the two men who shared the Nobel, who had changed the world together, spent their last 6 decades apart. Think about what that means. 32 papers, then silence. A collaboration that reshaped fundamental physics, terminated by a magazine article. The bitterness outlasted careers, outlasted decades, outlasted the Cold War. It outlasted one of them entirely, since Li died more than a year before Yang. The irony here goes deeper than personal tragedy. Li and Yang did not just discover parity violation. In their companion paper from 1956, they planted the seed of mirror matter theory. The idea that parity could be restored through mirror partners was their idea. They broke the symmetry and immediately proposed a way to fix it. If mirror matter is eventually discovered, if the invisible universe turns out to be real, then Li and Yang will have been right about both halves of the story, the breaking and the repair. But they never reconciled with each other long enough to see either idea through to its full conclusion. And then there is Wu, the woman who actually confirmed the broken symmetry. 26 Nobel nominations, 0 prizes. She designed the experiment. She assembled the team. She fought the superfluid helium. She got the result. And the two men who proposed the theory she tested got the call from Stockholm, while she did not. Wu never publicly expressed bitterness, at least not in terms the historical record has preserved clearly. She continued working. She became the first female president of the American Physical Society in 1975. She won the Wolf Prize. She trained generations of students. But Dale Hopps, who was there in the lab on those freezing nights in December 1956, who watched her fight for years to get the recognition she deserved, said simply that she probably regretted her absence to the last day of her life. She died in 1997. The Nobel Committee never corrected the omission. They cannot award prizes posthumously. These personal stories are not digressions from the physics. They are part of it. Because physics is not done by equations. It is done by people. People who cancel trips to China because they see a golden opportunity. People who sleep beside equipment waiting for the temperature to drop. People who improvise experiments with coffee cans and scotch tape and get 50 sigma results before Tuesday morning. People who write confident predictions 2 days after the answer has already been announced. Robert Foote spent roughly 30 years of his career on an idea that most of his colleagues considered a curiosity at best. He published about 100 papers on mirror matter. He wrote a book called Shadowlands that tried to bring the idea to a popular audience. He proposed that mirror matter could explain not just dark matter, but the Tunguska explosion, the Dharma signal, the close orbits of hot Jupiter exoplanets, and the anomalous cosmic ray events observed by various experiments. Some of these proposals were received politely. Others were received with visible skepticism. Howard Georgi's comment about Foote's work not attracting a huge following was diplomatic. Other reactions were less so. Foote's publication rate slowed significantly after 2016. He remains listed at the University of Melbourne, but the days of annual mirror matter papers appear to be over. Whether history vindicates him as a visionary who saw the answer decades before his peers, or as a talented physicist who spent a career on a beautiful idea that turned out to be wrong, depends on experiments that have not yet been performed. And then there is Pomeranchuk, who completed his last work 2 days before his death in 1966, the same year the mirror matter paper he co-authored was published. He proposed a form of invisible matter without knowing that invisible matter was the universe's biggest mystery. Fritz Zwicky had published his dark matter observations 3 decades earlier, but the Soviet physics community was largely disconnected from that astronomical literature. Pomeranchuk died having contributed to one of the most prescient ideas in modern physics, an idea whose full implications would not be appreciated for another 50 years. And he never knew. He could not have known. And then there is Beregiani, still alive, still publishing, still working at L'Aquila and Gran Sasso, still pushing for the experiments that could confirm or refute the idea he has spent decades developing. His student Diwali went on to direct the Max Planck Institute for Physics. His neutron oscillation prediction sparked an entire experimental program across 3 continents. And the answer is still out there, somewhere in the data that has not yet been collected. Let us come back to the central question one final time. Is there a complete invisible universe sharing our space right now? The honest answer, the only answer that respects both the evidence and the theory, is that we do not know, and we are closer to knowing than we have ever been, but closer still means not there yet. The case for mirror matter rests on 3 pillars. The first is theoretical elegance. Parity is violated in the weak force. This is experimentally certain. The simplest way to restore the symmetry at a fundamental level is to double the particle content of the universe with a mirror sector. This is not ad hoc. It is the minimal mathematical fix for a confirmed broken symmetry. Whether the universe cares about our sense of mathematical minimality is, of course, an open question. The second pillar is dark matter compatibility. Mirror matter naturally produces gravitationally interacting invisible matter with self-interactions that solve problems collisionless dark matter cannot. It was not designed for this purpose. It emerged from symmetry restoration and happened to match what observational cosmology requires. That coincidence is either meaningful or it is not, and no amount of theoretical argumentation can settle the matter. Only experiment can. The third pillar is testability. Mirror matter makes specific predictions. Neutrons should oscillate into mirror neutrons on timescales that current or near-future experiments can probe. The kinetic mixing parameter should produce signals in next-generation direct detection experiments. The self-interacting nature of mirror dark matter should produce measurable differences in galaxy formation compared to collisionless models. The dark disk, if it exists, should affect dark matter density measurements over long timescales. These predictions are concrete, falsifiable, and within experimental reach. Against those 3 pillars, the evidence column is currently sparse. No neutron oscillation signal, no dark photon detection, no confirmed direct detection of mirror matter scattering. The Dharma modulation signal appears to be an artifact. The neutron lifetime puzzle may be a systematic error. The Xenont and LZ-XS is tantalizing, but far from definitive. This pattern, strong theory, plus null experiments, is not unique to mirror matter. It describes the current state of the entire dark matter field. WIMPs have been searched for with extraordinary sensitivity for 40 years and have not been found. Axions have been searched for at increasing sensitivity and have not been found. Sterile neutrinos have been searched for and are increasingly disfavored. The dark matter problem is now over 90 years old, dating back to Zwicky's 1933 observation. And despite the combined efforts of the global physics community, we do not know what 84% of the matter in the universe is made of. In this context, mirror matter is not failing any harder than anything else. It is simply one candidate in a field where every candidate has failed to produce definitive evidence. The difference is that mirror matter was not invented for the purpose of explaining dark matter. It exists as a theoretical idea regardless of whether dark matter turns out to be its domain. There is a version of the next decade in which IBM finds a neutron oscillation signal, in which LZ or xenon NT, with more data and better xenon 124 modeling, confirms the high-energy recoil excess, in which the Vera-Rubin Observatory maps dark matter halos that show the velocity-dependent self-interaction signatures that mirror matter predicts and collisionless, cold dark matter does not. In that version of events, mirror matter goes from speculative to confirmed within a few years, and the entire history of the idea, from Li and Yang's 1956 paper through Pomeranchuk's final months to Foot's lonely decades of publication, becomes one of the great stories of scientific persistence. There is another version of the next decade in which H, I, B, E, A, M finds nothing, in which the neutron lifetime puzzle is definitively resolved as a proton counting systematic, in which galaxy surveys are perfectly consistent with collisionless dark matter. In that version, mirror matter fades from the landscape of viable ideas, joining the long list of beautiful hypotheses that the universe simply did not choose. Either outcome would be significant. A confirmation would be among the most important discoveries in the history of physics. The revelation that the particle content of the universe is twice what we thought, that an entire invisible cosmos has been sharing our space since the Big Bang. A definitive exclusion would close a 70-year-old theoretical avenue and redirect the dark matter search elsewhere. Science wins in both cases. The only losing outcome is the one where we stop looking. And it is worth pausing here before we close, to sit with the full strangeness of what mirror matter implies if it is real, because we have been talking about it in terms of experiments and parameters and sigma values, and there is a risk of losing the sheer vertigo of the idea. If mirror matter constitutes the dark matter of the universe, then every galaxy you have ever seen in a photograph is embedded in a halo of invisible mirror atoms. Those mirror atoms are not static. They are moving, interacting with each other through mirror electromagnetism, forming structures. The mirror sector has its own chemistry, its own version of the periodic table. It is dominated by helium rather than hydrogen, which means its chemistry is radically different from ours, because helium is a noble gas that resists bonding. But mirror matter still has heavier elements produced in mirror supernovae. Mirror carbon, mirror oxygen, mirror iron. These elements can form mirror molecules, mirror dust, mirror rocks. It is possible, and this is where even the proponents get careful with their language, that there are mirror stars burning mirror hydrogen in a mirror plasma, emitting mirror light that no telescope will ever detect, mirror planets orbiting those stars, mirror oceans on those planets. This is not a scientific prediction. It is a logical extrapolation of the theory taken to its limit. Foot wrote about it. Okun wrote about it. They were not claiming that mirror life exists. They were pointing out that the theory permits it, and that the theory does not draw an obvious line between mirror atoms and mirror everything else. The local dark matter density near Earth is roughly 0.3 giga-electronvolts per cubic centimeter. If those are mirror particles with masses around 100 giga-electronvolts, that works out to about 4 particles per cubic meter, moving at 220 kilometers per second. Roughly 10 trillion mirror atoms pass through every cubic meter of space near the Earth every year. They pass through walls, they pass through mountains, they pass through you, and they do so without leaving a trace. Because the interaction between ordinary and mirror matter is 10 billion times weaker than the force that holds your body together. If there is a mirror star within a few light years of the Sun, we would not know. If there is a mirror planet in the outer solar system, we might eventually detect its gravitational influence on distant objects, but we would never see it. The invisible universe could be far richer and more complex than the simple, featureless, dark matter halos of the standard cosmological model, and we would have no way of knowing until we develop instruments sensitive enough to detect the faint whisper of kinetic mixing that connects the two sectors. That is the promise and the frustration of mirror matter. It is the most maximalist dark matter hypothesis ever proposed, an entire parallel physics rather than a single new particle, and it makes the fewest demands on our ability to detect it. It is a universe hidden in plain sight, or rather, hidden in plain darkness. And that brings us full circle, back to Los Alamos, back to the magnetic bathtub, back to those 9 missing seconds. Sohrab Baregiani's explanation is still on the table. The J-Park result complicated it, but did not kill it, because the J-Park measurement used a fundamentally different detection technique and has not yet achieved the precision needed to fully resolve the discrepancy. The original NIST proton counting result has not been retracted or explained, and Baregiani's prediction, the varying the magnetic field profile in a beam experiment, should produce dramatic changes in the apparent lifetime if mirror-neutron conversion is occurring, has not been tested. The proposed experiment at the high-flux isotope reactor at Oak Ridge has not yet been funded or conducted. 9 seconds, roughly 1% of the neutron's total lifetime, a gap that has persisted for 25 years despite every effort to make it close, a gap that sits right at the boundary between probably a systematic error and possibly the first hint that particles are leaking out of our world. The measurement is so simple, it almost hurts. You put neutrons in a box, you wait, you count what is left. Someone else sends neutrons through a tube, catches the protons they produce when they decay, and counts those. The two numbers should agree. They do not. And for a quarter of a century, nobody has been able to explain why. There are mundane explanations still on the table. The J-Park electron counting beam result, which agrees with the bottles, suggests the issue might be specific to how the NIST experiment counts protons. Maybe there is a subtle efficiency correction that has been missed. Maybe the proton trap geometry creates a systematic that nobody has caught. These are real possibilities, and any honest assessment has to weight them heavily. The history of physics is littered with anomalies that turned out to be errors, but it is also littered with anomalies that turned out to be discoveries. The Tau Theta puzzle looked like a nuisance until Li and Yang realized it was a clue. The flat rotation curves of galaxies looked like observational errors until Rubin and Ford measured 21 of them, and the pattern became undeniable. The cosmic microwave background was discovered by two engineers at Bell Labs who thought their antenna had a defect. Sometimes, the universe hides its deepest secrets in the smallest discrepancies. We started this story with a question. Is there a complete invisible universe sharing our space right now, built from the same laws of physics, made of the same types of particles, running on its own forces, with its own atoms, its own chemistry, its own structures? The answer, as of today, is that the idea is consistent with every observation ever made. It has not been confirmed. It has not been ruled out. The experiments that could settle the question are either running or under construction. The universe is under no obligation to be as interesting as mirror matter theory suggests, but the universe is also under no obligation to be simple. In 1957, Wolfgang Pauli wrote with supreme confidence that the Lord is not a weak left-hander. 2 days later, he learned that the Lord is, in fact, exactly that. The universe does not care what physicists find elegant or plausible. It does what it does. Maybe there is a shadow cosmos out there right next to ours, built from the wreckage of a broken symmetry, invisible and silent and vast. Maybe the dark matter that sculpts every galaxy and bends the light of the cosmic microwave background is not some featureless fog of inert particles, but a living, structured, chemically complex mirror world, complete with mirror stars and mirror elements and mirror helium oceans on planets we will never see. Or maybe the mirror is just a metaphor, a beautiful theoretical construction that the universe chose not to build. The people who have chased this idea gave it everything they had. Wu gave up her first trip home in 20 years to shatter a symmetry. Li and Yang gave up their friendship. Pomeranchuk gave his final days. Foote gave his career. Bereziani is giving his still. And 68 years after a woman in a laboratory in Washington proved that the universe distinguishes left from right, the fix that two young theorists proposed that same year, the mirror that would restore the symmetry she had shattered, may turn out to be not just an idea, but the architecture of everything we cannot see. We are still looking.